welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Bourkas. I am very much looking forward to our next presentation regarding the topic improvement of dynamic behavior of the evaporation process within a molten carbonate fuel cell humidifier. Please welcome with me on stage Dr. Jean-Paul Janssens from BOSAL Energy Conversion Industry.
Thank you.
Thank you.
Okay, good afternoon. So I'm today going to talk about the dynamic behavior of an evaporation process within a molten carbonate fuel cell humidifier. To focus somewhere where it is, you see here the type of fuel cells. And you have on the top the high temperature fuel cells. On the bottom you have the low temperature fuel cells. And BOSAL is active in the high temperature fuel cells. Now, we have a lot of applications within the solid oxide fuel cell. Today we're going to talk about the molten carbonate fuel cell. Now, how does that work? So that is a fuel cell where the carbonate group is mobile and with hydrocarbon fuel, let's say methane, mixed with steam, you can make electricity as you see it over here. Now, the humidifier is the component that evaporates the steam and humidifies the natural gas. So it is located upstream of the anode flow. To do that, you need heat. And this heat you extract out of the cathode flow. So the cathode flow has here a temperature of 560 degrees. And that is used to heat up water at 15 degrees C and the natural gas and mix it up to 400 degrees C. Now, that means that you need a counterflow heat exchanger. So you have to heat up both. You have also the latent heat, and you want to reach this temperature. And then we speak about effectiveness. So if the effectiveness is as high as possible, 100%, then this temperature reaches this temperature. Otherwise, now in this relation, you have a lower effectiveness. Now here you see a graph of what the effectiveness is in case of, for instance, an ideal counterflow heat exchanger. So you reach, in fact, 100% effectiveness in theory if you build a big heat exchanger. In practice, it is not the case. So you see here the mass flow. So if you go to higher mass flow, effectiveness goes down. But due to thermal conductance over the ideal heat exchanger, you see that you reach a maximum. And if you have not a good counterflow heat exchanger, you only can reach 70%. So you have to deal with that. And you see that the BOSAL components reach somewhere here in the vicinity 90%. What we make is this type of system. So this is the humidifier. So it is designed to heat up natural gas, mixing it with steam. And that is built out of 7 cassettes for a kind of modularity. It is built, tested at BOSAL and also at the customer. What is the background? Well, BOSAL is known as an exhaust manufacturer. And we are a global player, as you can see. We are active in multiple continents. And it is based on that knowledge that we now develop a humidifier. And it is in fact a product derived from an evaporator for a Rankine cycle. That is used for waste heat recovery in internal combustion engines. So you can see here, well, the exhaust of an internal combustion engine, you evaporate, you expand over an expander, and you make, in fact, power with those units. Those units have the characteristic that they have a low back pressure, very effective heat transfer, modular based. You can use it at high pressure, up to 60 bars at 600 degrees C, and you can even run it dry. We do this simulation sizing and design, in fact, based on different systems and knowledge. So we do it in 0D, that is spreadsheet based. We can do dynamics, and therefore we use our commercial software, our own developed MATLAB codes, or we use CFD. So we have also testing capabilities. So we have done thorough testing of these evaporators based on this type of system. And also not only performance, but also dynamics. And we also did certification. So these units are certified according to the European Pressure Equipment Directive or the AD 2000 German legislation. And it is built up as components, as you see here below. Now, these components are used. So here you see the unique selling propositions of these units. These are also in the market. So we gather information and knowledge about the field, in the field, so where the user applies those units in reality. And important is that you can use these units also what we call misuse. That is in fact drying hot, running dry and hot, and then injecting water. Now, if we are lucky, you can see this. So that is regarding endurance. There is here a movie in which we can see the beginning of the evaporation. So the unit itself is fed with 600 degrees hot air, so it is red hot, and you inject water. So that is in kind of water quench, and that is done 3,600 times. And then you see this. I think, does it work? I'm not sure. No. If we can you start? So you see, if you start the injection, you immediately get steam. So that is a very tough test for this type of applications, and you can see that we can do that 3,600 times, which is sufficient. We have also a production facility in the Netherlands where we can make those cores and build them together, for instance, up to this type of unit. This is a 1 megawatt unit. So you see it is rather compact for 1 megawatt, so it's 1 meter on 1 meter, or even less. Now about dynamics. For this application, the customer had special requirements. So his requirement was that the fluctuation of the mixture should be as low as possible, less than 5 degrees within 30 minutes. To do that, we used our knowledge about exhaust systems. So this is the approach, the transfer matrix approach of an exhaust system or an inlet manifold. So people from automotive recognize this as well. So inlet manifolds are designed based on this type of matrix for a pipe, so that, for instance, this can be simulated as one pipe and another pipe, simplified here to the tube, and here to the volume. So here you just neglect the cosness because it is small, so then you have one, and here you see these simplifications. We also embedded then impedances, and you can use this, for instance, as an example. This is how you do it in an exhaust system, and you project this knowledge on an evaporator. So what you do is you control the transfer function of such a system. And what did we get? Well, we designed this type of system. So here you see the complete unit. So the hot air is going through the system. You see the inlet of the natural gas and the water, and the mix out. In such a cassette, what you see here, you have different modules, where you have a counterflow system, and you have tubes, the feeding of the natural gas, of the water, and the mixing areas. And the result is that you generate a dynamic behavior compared to what you saw a minute ago. We did tests, and the test unit itself is here on our booth. And what you see here is the frequency response, so the transfer function of the frequency. And you see here, this is a factor 10 always, and that is also a factor 10. So here in the beginning, we have an inclination of 40 dB per decade. So that is a real steep cut-off. While then here you get resonances, but in total you have 20 dB per decade. So it is a very good, stable system. We realized that in full, because the first one that was a prototype, we realized that in full and we tested that on the system. And as a result, we come then to the conclusions. So the performance regarding effectiveness and pressure drop was okay, and the stability was better than the expectations. So normally we should reach 5 degrees, so we had ±1 degree over 30 minutes, where the competitor has a fluctuation of 70 degrees. So you see, regarding lifetime of that molten carbonate fuel cell, this has an enormous impact. Regarding endurance, we did trip tests, so cutting off, in fact, and starting again. And also there we were far above the requirements. So that is about molten carbonate fuel cells. We have also other balance of plant components. For instance, yeah, so what we discussed now was the tube application. We have also plate applications for solid oxide fuel cells. And we can apply coatings or mixers for reformers and afterburners. So with this, I would end the presentation and welcome you on our booth. Thank you.
Thank you very much for this presentation, Dr. Janssen. Are there any questions right now from the audience? Okay. You've shown at the end the conclusion or the results.
Yes.
What is the outlook? What is next?
The next is building these units and install them in field. So and gather information in the field.
You're doing this by yourself, or you are partnering on doing collaborations?
We do it ourselves, and we deliver it to our customer directly.
Okay.
Yeah.
Good. So good luck with the next step on
Thank
this.
you.
As you already announced, please visit them at their booth D55.
52.
Sorry, 52. And yeah, so we will have the last presentation of today. It will be regarding use of simulation methods in the development of alternative drive concepts by AVL List GmbH. Afterwards, we will finish with the presentations, but at 3 p.m. there will be an elevator pitch, or rather 10 elevator pitches. So don't go away. I think it will be very entertaining to see the elevator pitch after the last presentation starting in a few minutes. Thank you very much.